So last class we talked about analyzing multiplicative weights. We showed the regret bound, which was square root t times ln d with a particular choice of epsilon. And then we also started looking at applications of multiplicative weights. And the first application we started studying was to optimizing functions on the simplex. It was kind of a variant of gradient descent, where instead of doing like an additive update in gradient descent and stochastic gradient descent and so on, we are looking at some kind of multiplicative update based on the gradient. So today my goal is to do one more application of learning with experts framework, and then we'll start the next module, which is principal component analysis. And a couple of announcements. The first one is that assignment 2 is due today at 10 p.m. on Gradescope, so make sure you do that. And also I posted a link for a course feedback form on EdSTEM. If you can fill that out, that would be very helpful in trying to kind of tweak the even the content or the various ways we're using the platforms in the course. Okay, so any feedback would be very helpful. Okay, so going back, so we looked at this, we were given a function f on the simplex, which is set of all points or probability distributions, and it was convex, and we showed that if we used kind of an algorithm based on multiplicative weights, we could find an approximate optimizer, something which gets epsilon close to the optimum, with only log d over epsilon squared iterations. And the notable thing here is that if you used just plain projected gradient descent, for this specific set of functions, then you get a bound which is linear in the dimension as opposed to logarithmic in the dimension. So it's a very substantial improvement, right? And the algorithm was a bit mysterious, but I think actually it's not that. I made it a bit more mysterious than it should have been. The main thing here is that instead of doing gradient descent, where when we do gradient descent, the update looks something like this: minus some step size times gradient, right? So the main idea here is instead of doing this, you do some kind of multiplicative update. And the proportionality sign is because you have to be on the simplex, you multiply all the coordinates and then you rescale them so that you add up to 1. Okay? And you need to tweak this multiplication factor a little bit so that you never become negative, and that's what this small additive shift is. Okay? So any questions about this algorithm? I mean, it's kind of a strange way to analyze it. So this is a very straightforward algorithm to describe. You can say, okay, it's a multiplicative version of usual gradient descent, but then to analyze it, we use the regret framework while learning with experts. And that's something like a trick that you often see, where even in problems where there is no learning with experts per se, you sort of use the framework to analyze other algorithms. Okay? Any questions about that? If not, let me kind of give one more very important application of this learning with experts framework, and this time it will be for boosting. So let me go back to my notes there. Okay. All right. So what is boosting? Maybe some of you have already seen boosting, but boosting is a really important tool in practice. And at its core, it addresses the following question, right? Suppose you're trying to solve some learning problem, some prediction problem. And your goal is usually to get as high an accuracy as you want, like pretty high, like let's say 90% or something like that, right? But maybe to start with, you don't have an algorithm which gets you 90% accuracy, but you have some sort of black box which gives you some advantage over random guessing. Right? So, I'm trying to predict, let's say, binary classification problem where the labels are 0 or 1. And so goal is to get 90% accuracy. And I mean 90 is like, just a placeholder for high accuracy. It could be 99, 95, whatever, like some number which we think is higher than what we are starting with. And what we have is like a weak learner. We don't know how to get 90% accuracy to begin with, but we can get 60% accuracy. Okay. So this is what we want, right? And this is what we have. Okay? Does it make sense? So the question is whether we can use this sort of ability to get 60% accuracy in a black box way to get 90% accuracy. I mean, what you can ask whether, okay, if you have 60% accuracy, maybe I'll dig into the algorithm and do some massaging, some parameters, some tuning, use some additional ideas to boost it to 90%. But it would be even nicer if there was some sort of mechanical way of taking algorithms which get 60% accuracy and push them all the way to 90% accuracy. Okay, so this was the meta question that people asked long back. Can we boost weak learners to strong learners? Right, so weak learners here just means, algorithms which get slight advantage over random guessing. And since this is a binary classification problem, random guessing would give you 50%. Getting 50% accuracy is trivial, right? I just output a random label, it will be correct 50% of the time. You have slight advantage over that, and now you're asking, can I boost it all the way to very high accuracy? And we can study this in the PAC framework that we talked about in the first lecture, and that's where it was originally posted. But formalizing it there takes a little bit of work, and you have to do some statistical modeling. So let's not do that. But let's study a version which is still very important in practice and captures the essence of the main problem. And that is what I call boosting on our samples. Okay, so let me explain what this means. So the meta question is, can you boost weak learners to strong learners? But let's formalize this question a bit more rigorously. Right? And the best formalization is in the PAC framework, but I'm saying, it's kind of a bit more cumbersome. So let's do something which is easier to get to. So suppose I have some data set, right? X1, Y1, X2, Y2, and so on, X and Yn. Okay? And these are coming from some domain. You can think of it as RD, and actually, we have to change notation. Okay, and this is some domain. It doesn't matter what the domain is, and this is some label space. It doesn't matter what the labels are. Okay, so we have some data set and we have some hypothesis class H. Okay, and we called path learning framework. We said, okay, you have some hypothesis class. My goal is to find some function from my hypothesis class which can explain my data set. So goal, find H belonging to the hypothesis class that explains the data set the best. Okay, so meaning, find H belongs to the hypothesis class such that right, so you want to minimize the probability or the number of actually let me write it this way. So the number of the fraction of labels that the fraction of examples that you misclassify. Okay, so a little bit like empirical risk minimization, where your parameter space is given by this hypothesis class H, and the loss you're looking at is just 0, 1 loss. Are you correct on the example or not? Okay, so suppose this is my goal. It's kind of a version of empirical risk minimization. And but this is sort of standard, but the crux is now I'm telling you, I'm giving you this magical ability to do the following, which is to find a weak learner. Can find a H such that fraction of mistakes is let's say less than or equal to gamma. Think of gamma as something like 0.49. Okay, so I'm correct on 51% of the samples. Right? And the goal is, can I find another hypothesis that does better? Okay, does this question make sense? I mean, it seems silly to ask this question even, right? If I just tell you can get 51% accuracy, how can you just boost it to something higher, like, let's say 90% accuracy? Do you think it's ever possible? Yes or no? Well, it shouldn't be possible if I just tell you all you have is a single hypothesis that gets you 51% accuracy, right? Then, that's all you have. You can't do anything better, right? But what would be a nicer way to formalize this weak learner assumption? Any suggestions? Like, we need to strengthen this weak learner assumption just a little bit to make this question meaningful and powerful. But what should that just a little bit? I shouldn't say just a little bit, but conceptually is just a little bit. Any guesses? Right, so there's a question, are we still stuck with one weak learner? That's the core of the problem. Like, somehow if I just stuck with one weak learner, you cannot really use it. But imagine that, something like the wisdom of the crowds, right? So let's say you have some, you have the entire course. There's like, 5 modules. Each one of you does somehow very good on one module, right? Then maybe together you can do well on the entire exam, okay? But then how do you capture that each one of you covers kind of a different portion of the syllabus and is doing very well on that portion? We need
So now,
something
like,
like that.
if you have 2 hypotheses from the class, I mean, you have to somehow be able to like connect them, like take like a union of them somehow. Like,
But also you need to change the weak learner assumption, right? Like if I tell you that each one of you is doing well, but all of you do well only on the first portion of the syllabus, you're not going to do well in the entire exam, right? Because the other portions are not covered at all. Even if you can pool your resources, you won't be able to do well because all of you are doing well on some segment. So the question, what is the assumption again? So in some sense, we are trying to figure out what the right assumption should be for making this boosting question meaningful. Like you want to say, okay, you can do some weak learning, then you can go high. So it's like wisdom of the cross. Like suppose that there are 1,000 people and you're trying to get, you ask everybody what is my weight. Everyone has some 51% accuracy towards guessing my weight. You take the majority, you assume that it will improve the accuracy. Right? So when is that true and when can we actually make it rigorous?
Would you need some kind of independence assumption where the errors that they're making are not correlated?
Exactly. So that's kind of that's what we really want. Somehow we want the ability to get weak learners who behave differently. They're not making the same mistakes, right? And kind of seems like a sort of a thorny issue to formalize. How do you make it rigorous, right? But fortunately, people in the 70s, especially Valiant, formalized this in a very clean way, and which is what we will use. So the assumption is the following then. So we're going to change the assumption to sort of capture the fact that our weak learners can focus on different parts of the data set in some sense. So in particular, so maybe you can say, if I take any subset of the data set, then I can still find something which gets 51% accuracy. Right? If I knew that, maybe I can use that to capture the whole space. Right? So suppose I tell you that you take any subset of lectures, and if you make an exam on that, one of you can get 51% accuracy on that. Okay, so maybe then you can pool all your resources together to do 99% on the whole exam. Okay, so that's the kind of setup. So the assumption is going to be that for every distribution D on the samples, okay, you can really only work with just subsets, but working with distributions makes things easier. We can find a edge such that the number of mistakes you make is at most count. Okay, so this is our assumption now. So meaning I can pick sort of any subset of my data set, my subset of samples, and even within that subset I can find some hypothesis which does 51%. Okay. Does it make sense? So somehow it's not as if all my weak learners are good on some small fraction of the data set and they're not learning anything about some other fraction of the data set. Right? I always have the ability to get some advantage of random guessing on any small segment, or in fact any other distribution on the samples. Right? And just to make things clear, when I say distribution on samples, the samples are just x1 through xd, yd, right? So I just have a distribution and indices 1 through d. Okay, I can change kind of the distribution on these d examples, and even then I can find a hypothesis which gets me 51% accuracy. That's my weak learner assumption. Okay? And our goal now is can I find a simple hypothesis, G, a strong learner, such that the fraction of examples, oops, this should be D, okay? So I'm going for something which is 51% accurate to something which is 99% accurate. Okay, does the question make sense? It's a very sort of subtle way to formalize this, but it can be done. Any questions about it? Okay, so this question of boosting a weak learner to a strong learner was posed by Les Valiant in the 1970s, and it was a major open problem in learning theory. And so it was asked in 1970s by Valiant and others. The first solution. So first of all, it's not even clear that this is possible, right? Forget doing it computationally efficiently, forget actually doing it with an algorithm. It's not even clear that this should even be possible, right? And Shapiri in 1989 solved it. Okay, and then it was kind of very interesting theoretically, but then Freund and Shapiri in 1995 gave a practical algorithm. Like a very simple, 5 lines of code for doing this. And this has been amazingly useful in practice. You can build all kinds of classifiers, very good classifiers, just based on this. Because all you have to do is to come up with something which gets some advantage over random guessing. Right? If I can come up with any algorithm which gets me, 51% accuracy, just like 0.1% accuracy advantage over random guessing, then I can boost it all the way. Right? I can just call this boosting algorithm which takes my weak learner as input and outputs a strong learner. Right? And so they introduced this algorithm called Ada Boost. And that is what we are essentially going to see today, that how to use Ada Boost to achieve this boosting goal. And so just to give you an example of this in practice, So in 2005, two researchers, computational vision researchers, Paul Viola and Michael Jones, they designed what is called the Viola-Jones face detector. So the problem they were trying to solve was, I'm given, my goal is to detect faces in pictures, right? Like for instance, if I go, let's say here, if I upload a picture like this, I need to put boxes around every face in the picture, right? And you can see, well, there's a mistake here, but you can see that it's pretty accurate, right? The system that they're building. And it seems quite common, it seems amazing that they're doing this. This is 2004, so it's even more impressive given the hardware they must have been using. So what did they do? They used something called decision stumps. So what's a decision stump is something, a very simple classifier which looks at one or two features in your vector to make the decision. They said, okay, I don't know how to detect faces, but let me do something very simple. I'll try to detect eyes in the following way. I'll try to look for a box where the top portion is darker than the bottom portion. Like a small rectangle where the top half is darker than the bottom half. Can anyone guess why that might do slightly well in detecting pictures? Just heuristical. Well, okay, their reasoning was that eyes are usually darker than the cheeks. Like, when you take a picture, eyes might be darker than, your cheeks. Right? So that's sort of one simple way to classify faces. The other thing they used was this sort of dark, bright in the middle. Can anyone guess why that might be a good way to find pictures, to find faces in an image?
Is it again with the eyes? Yeah,
The
like with
eyes,
the nose.
exactly. Nose might be brighter than the eyes, right? These seem like simple rules, but basically none of these rules will give you very high accuracy. You take any database of images, these rules might be good for 51% of the pictures. Right? They'll do better than maybe random guessing, but they'll make a lot of mistakes individually. So what they did was they designed such simple filters, and then they just, you can see what they're doing here, right? Do you recognize this algorithm? Normalize the weights, update the weights, and do something. Right? I mean, essentially they're doing boosting. They said, okay, these are my simple weak learners, and I'll boost that using my boosting framework. And they basically improved the state of the art in face detection by almost like an order of magnitude by this simple trick. Right? The final thing is very easy to implement, and it was a very important paper in vision, showing that you can get such high accuracy using a very simple algorithm. Now we have much better face recognition stuff using deep neural networks, but this is still an important step at some point. Okay? So in general, the point here is that it might be easy to come up with rules which do slightly well, right? And boosting allows you to combine them without worrying about how you're coming up with these rules in the first place. It's kind of a black box meta-learning algorithm. Okay? All right. So let's go back to how to do boosting. And if you know what random forests are, they are also a little bit like boosting, where you use maybe I have 1 million features, I'll focus on 10 features which give me some advantage, and then boosting, you run boosting on top of that. Okay? Alright, so how do we do boosting? So the main thing is, once you get the conceptual idea, the analysis is not that complicated, especially given what we've done in this class. So I won't stress the analysis, but I want to emphasize the algorithm and nothing else. So what can I do to take advantage of the weak learner here? What's the main lever that we're going to use to build a strong learner? Any guesses? So once we get the main idea here, like what we should try and exploit, and then figuring out the details is sort of not that hard. But we need to make one leap in terms of trying to come up with this idea. So what's the ability of the weak learner, right? So imagine this is my whole, this is data set, right? This is 0.1, 0.2, 0.3, 0.4, and these are my, D examples. So really just a set. Okay? And always think of the weak learner as something which gives me a hypothesis which is 51% accurate on any subset of the data set. You give me all examples, I give you something which is 51% accurate. You give me some subset, like let's say of half the size, I'll give you something which is 51% accurate on this half the size. Right? So let's say I don't know anything to begin with. So maybe initially I just pick the entire data set. Okay, I ask the weak learner, give me something which is good on this entire data set. Right? And weak learner says, okay, here's something. How many points do you have? 1, 2, 3, 4, 5, 6. Okay, so here's something. Right? And the weak learner gives me a hypothesis, tells me that, okay, you're wrong here, but you're correct on these 6 examples. Okay, so you're correct on these 6 examples, you're wrong on these 5 examples. I asked my weak learner, give me something which does well on the entire data set. It gave me something which slightly better than random guessing. It's not even clear if it's better, but it got one more correct than it got wrong. So what can I do now? What should I make the weak learner do next? So we have this black box, right? This library which always gives out a weak learner whenever I ask it on some subset of the data set. So what should be the idea then?
If you know which examples you got wrong, you could define a weak learner on that subset.
Exactly. And we know which examples we got wrong, right? Because we have the xi's and yi's. And that's kind of why we are using the boosting on samples framework, because it makes this question easier to answer, right? So we know which examples we got wrong because we know these are the xi's and yi's, and we can check, is h of xi equal to yi or not? So for the second query, it makes sense to focus on the mistakes that you made, right? So here's where we made the mistakes, and we should focus on that. We should ask our weak learner to run on the mistakes that we made. It's, the ideal way to train for a final, right? You look at your first, let's say midterm, we don't have midterms, but you look at your midterm, wherever you got mistakes, you try to study that portion more and then kind of keep revising it, right? So that's exactly what we are going to do. So the idea is start with the distribution. So we are going to pick distributions to query the weak learner on. So let me say,
Professor,
yeah.
in this picture, what you're saying is that we're gonna have the weak learner study the ones that I got wrong more, or
Right. So basically, the first time we queried the weak learner, it made these mistakes, right? For the second query, what I'm going to do is ask the weak learner to give me something does well on these red examples. Okay, and it will give me some other hypothesis H2, right? It says, okay, this is, H1, and now I have H2, and maybe it does, so there are 5 here, so it is maybe right here, and wrong.
And it's the same weak learner that's doing this.
The same weak learner, but weak learner is a meta algorithm, right? So it gives me a hypothesis. So, but it can be a different hypothesis. It's a completely different hypothesis. This is H1, this is H2. So all I know about H2 is that it does better on this, yellow samples that I gave as input. I don't know how it is going to do on the green samples. It might be completely wrong on the green samples, but somehow I want to combine these things.
So our overall hypothesis will be H1 and H2 at this point.
It's not clear if I do H1 and H2, or maybe I should be a bit more clever about it. So we haven't answered that question so far. So the main thing we at least decided on is we need to query the weak learner on things that we're making mistakes on, like in successive iterations. But it's not clear how to combine it.
Okay.
Okay? All right. So what's our assumption? Our main assumption is that given any distribution D on the samples, I'll think of it as a distribution on 1 through D, just the indices. If I call the weak learner D, we get okay, so this is our sort of, a function that we have implemented. So in a boosting framework, this is exactly what you do. If you look at any machine learning library, there will be boosting meta algorithms that you can call. They'll say, okay, you have to implement, like just as in gradient descent, we had to implement the gradient function and then we could pass it to the gradient descent and it did something. In boosting libraries, you just have to implement this weak learner, give a handle for this weak learner to the program, and it will give you some other thing. It will do something and it will give something which is presumably a strong learner. Okay? All right. So this is our assumption. We have this sort of library call which will always give us a weak learner. And the idea is, initially start with the starting distribution being uniform. Okay, so here I'm thinking of the distribution that we're working with as a vector of probabilities on 1 through D. Okay, it's a bunch of numbers which are non-negative and add up to 1, right? They give you a distribution of the samples. And so we query right, and for t equals 1 through t, update dt. Okay, so this is the template. Maybe I just completely throw out the things that I was right on, and my next query is only on the things that I was wrong on, right? That would be one way to focus. But then you might sort of have run into problems that H2 doesn't have much accuracy or any information on the green samples. So maybe there's like a middle ground you can choose, right? So I start with some distribution, I get back a hypothesis, and based on that hypothesis that I got back, I can update my distribution, and then I compute another hypothesis, and so on. Okay? And the final thing I had to do is combine, so let's say H output H strong, which is some way of combining all the weak learned hypotheses that I have reached. Okay, so this is pretty much the template that we naturally end up with if you try to use the weak learning assumption. Right? You made some mistakes. I want to change my distribution to maybe somehow make the weak learner focus on these things, give me more information, something which is more accurate on these things, and repeat. Does this remind you of anything? Yes, no? Right, so this is basically the boosting template, and the question is, how do you update? So we have to answer two things. One is how do you update, and the other is how do you combine? Okay, and we need to decide how to do these two things, and also what does it even, like, what can you actually guarantee here? What's the best you can hope for? Okay, so let's take a 5-minute break, and when we come back, I'll tell you how to do this, and hopefully you will yourself tell me how to do this. Okay, so let's resume at 10. Okay. All right, so now we have this boosting setup, and I want you to tell me, somehow this should already trigger some kind of pattern matching in your brain, right? Like every time you see something like this, I want you to get to a stage where you can do pattern matching. So I want to update some distributions, and then I want to combine. So what would be a natural way to do this? From here on to the end, in all your career, whenever you say update distributions, what should be the first thing you should think of? Come on.
Can you repeat the question? I don't know if.
So I'm saying.
I want to
here
say
we're
it's
saying-
like the previous combination of experts, sort of similar, where the experts are these hypotheses, but I don't know if that's what you're asking.
So basically, whenever we see updating distributions, right? So we're starting with one distribution, and then we have to update the distribution to get something else, right? And I'm saying when you see such a thing, multiplicative weights or multiplicative way to update distributions is a very natural thing to try. Okay, so in particular, I can think of updating the distributions based on the multiplicative weights algorithm. Right? So what I'm going to do now is set up an imaginary learning with experts game, and I'll use whatever way the learning with experts with multiplicative weights tell me to update the distribution as the way to update the distribution here. Okay, so imaginary learning with experts game. So what should the experts correspond to? So think of our intuition here, right? So somehow we said when you make mistakes, your first hypothesis made mistakes on some examples, you wanted your next distribution that you're going to input to the weak learner to give more weight to the mistakes and less weight to the ones that you're correct on, right? So what should the experts in our game correspond to? What could they correspond to?
The H's.
No, right? I mean, so H is a single hypothesis that we're getting. But what are we tweaking things on here? These are the examples. This is, maybe x2, y2, x1, y1, and so on. Right? I made some mistakes on some examples, and for my next query to the weak learner, the next black box query I make, I want it to increase the weight I give to a subset of these examples. So in learning with experts, we work with distributions on the experts, right? We maintain a distribution on the experts. We pick an expert according to that distribution and then predict according to that, right? And here we have to maintain a prediction, like a distribution on examples, right? So there are d coordinates and there will be d experts corresponding to each example. Okay. So I'm going to run an imaginary learning with experts game where the experts will correspond to examples. Okay, so I mean the setup is counterintuitive, but once we get it, we can use the regret framework to do the grunt work for us, to do the heavy lifting of designing the algorithm for us. Okay, so I start with viewing each of these examples as an expert. And now to define the learning with experts, I need to come up with a sequence of losses. So D0 was the uniform distribution. Okay. And H0 was the weak learner that we got on coming from this guy. And so, maybe H0 tells me that, okay, you're correct here, wrong here, correct here, maybe wrong here. Okay, and intuitively, my next distribution that I query the weak learner on should give more weight to the examples that I was wrong in the previous round, right? So that you basically you train on the things that you're making mistakes on, right? So if probability is your weak suit, you should keep practicing probability until you get good, and then you check your state, and maybe then you start making mistakes in linear algebra. You go back to linear algebra and train on that, and then you start making mistakes on maybe algorithms. You go back to that, and it's like a cycle, right? So somehow you want to increase the weight that you give to the red examples. And I want to do this using the learning with experts framework. So let's say I want to give some losses which will make me do this. What should I give losses to?
The correct examples?
Exactly, right? So I'm going to say that here are my losses. The correct examples will get a loss of 1. The wrong examples will get a loss of 0. What would the result of this be? Basically, the experts framework, the multiplicative weights algorithm, will bump up the weights of things that you have losses on. Sorry, that you have no losses on, right? So it will bump up the weights of things that you are wrong on. Okay? define L okay. So basically, I start with these two things, and for t equals 1 through t, I define the loss as this way, right? It's 1 if I'm correct, 0 if not, so that I bump up the weight of the things that I was wrong on, and then, you just update right, I just use, actually, let me write it in a nicer way. So MW weights per MWM, I update the weights with these as my losses. And my next distribution is DTI. That's it. Okay, so this is my full sort of okay, so this is my, oh, it's too small maybe. Okay, let me keep it this way. So this is my boosting algorithm. And all I did was kind of reimagined the boosting question in the learning with experts framework. Right? And the powerful aspect of this is that once you set up this connection between learning with experts and boosting, maybe 5 years down the line, you come up with some other algorithm for learning with experts. Maybe not multiplicative weights, but something else. You can use that for boosting just by this translation. But anyway, so this is my entire boosting algorithm now. And this is exactly what I showed in the Viola and Jones paper, right? In this phase detection algorithm, the update was, pretty much this guy. Let's confirm that. Okay, where is the algorithm? Yeah, see. So you have the examples, and then you update the weights, and the final hypothesis. Right? So they're using exactly this boosting algorithm. Any questions about this?
Can you explain the 1 over d again? D0, that distribution part.
That's just the starting point. You can really start with anything. We're just starting with the uniform distribution because, initially there's no reason to pick any particular subset.
So in this case, you're applying 1 over d to each data point?
Yeah, so that's my distribution, right? Like, the way I'm counting errors is I'm asking each, to give equal weight to each example. Okay. And I mean, like, even this distribution part is like, you're just using it as input to the weak learner. So what does a weak learner do? It takes a distribution on examples and gives me a hypothesis which is partially correct under this distribution. Okay. And if that's kind of seems counterintuitive, you can think of giving the weak learner a subset of the examples, and it gives me something which is 51% accurate on that subset. So D0 is 1 over D, 1 over D corresponds to giving the entire set of examples the first round, and then we kind of refine it as we go along. It's not exactly what we're doing, but more or less, yeah?
How do you make sure that these hypotheses are not, like when they fix those data points that have less weight on them, sort of, how do you make sure that them training just on those doesn't mess up the other ones that were...
Right. In fact, it will. We haven't yet answered how to combine the things.
Okay.
Okay, so that's something that we have to address. But before that, there's a very important question in the chat. So the question is, if you want to make predictions on the examples using weak learners, so here we are assuming that we already know the yi's. Okay. If we already know the yi's, then why can't I just get this absolutely perfect algorithm which just outputs the yi whenever I want? Okay. And this goes to something like memorization versus a generalization, right? So if I just remember everything, then we won't be able to generalize to unseen examples. So that's why when I said goal, there was this simple here, right? And that simple word is very important. Our goal is not just to, I didn't quantify it because I didn't want to go into, I just wanted to stress the algorithmic idea and not going into the statistical learning theory part, which tells you why this should actually work and why this is a meaningful thing to do, right? We want something which is similar in complexity to the weak learners. I train something with using decision stunts, which is like 3 futures at a time. And I don't want your strong learner to be like, a 10-layer deep neural network. It should be something of similar complexity as the weak learner. And the reason we want that is that, we want it to generalize to unseen examples, and simplicity is one way to ensure that. Does that answer your question, Derek? Okay, so let's hope that it does. All right, so now what else can we do to finish the algorithm, right? So I told you how to update the distribution, and how do I combine? So at the end of the day, I have to give a single learner, right? I'm computing all this iterative hypothesis, right? I get H1 here, maybe this is wrong here, right here, wrong here, right here. Maybe it starts doing better on the wrong examples. And maybe this is H2. So on all the way up to HD. Okay, so maybe here I'm right here, right here, right here, wrong, wrong, and things like that. Okay, I keep revising on which examples I'm right and wrong, but at the end of the day, I have to combine my hypothesis, my H1, H2 to a single predictor. How can I do that? So basically think of the face detection example, right? My one weak learner was just this box, kind of rectangular box, which looked for eyes and cheeks. The other one was eyes and nose bridge. And maybe the other one would just be look for lips somehow, or facial hair, or things like that, right? And each of them gives me some idea. I need to combine these predictors into a single one. So how do I combine? Any guesses? What's a natural way to combine the hypothesis?
Like, I was thinking weighted sum.
Yeah, exactly. exactly, right? So I mean, it makes sense, right? Each one of you has now hopefully is correct 51% of the time, right? And we are assuming that somehow the mistakes are no longer correlated with each other, right? Somehow there is some independence between them. Each hypothesis is kind of good in some sense. So if we are already at that stage, then combining them by like a weighted sum makes sense, right? Why not? So that's exactly what we'll do. And so output, instead of the weighted sum, we can even just look at majority of h0, h1, all the way up to ht minus 1. Okay. So this is our boosting algorithm. And this is Ada boost. It's a very important algorithm in learning theory and in machine learning. It's often not the best you can do, but like it's somehow almost like the best bang per buck you can get in terms of simplicity to getting accuracy. Okay. So this is the full algorithm, right? So I start with D0, something like this. H0 is a weak learner, and I start updating the weights based on. So maybe I should say it's just 1. Okay. And the final hypothesis is the majority of the hypothesis. Any questions?
So the way this algorithm is working is like it's creating a bunch of weak learners on different distributions, and then when they agree, like that gives you like a stronger guarantee on like the prediction. So that's why the accuracy goes up.
Yeah, I mean, it's not even as if when they agree, but it's basically assuming that each one gives me tiny advantage in getting right. Now I get a new example, x comma y. H0 is correct with some probability. H1 is independently correct with some probability. I mean, it's very heuristic, this reasoning. But if I tell you that there are 1,000 predictors, each one is correct independently, let's say 60% of the time.
Then it's likely that the majority of them will be correct.
Exactly. Then the majority will be highly accurate, right? It'll be almost like exponentially close to being correct.
Okay.
Okay, so that's the reasoning. That's the intuition, and it actually works. So that's the algorithm, and let me state what is known about this. So theorem, Ada boost. Let me put it in quotes because we'll find H with a T which is actually, hold on. Oh, sorry. Yeah, that's it. Okay, so let's parse this for a second. So it's saying, suppose I want my final thing to be correct on all but a 0.01 fraction, right? So imagine I have a million examples and I started out with gamma being 51%. So my initial accuracy was 51%, so gamma is 0.49. It's tiny advantage. Okay? Then, and my goal is delta is 0.01. Then how many iterations do you need? Basically something like 2 times log 1 over 100, which maybe is like 9 divided by 0.01 whole square. So this is something like 10,000, right? So after so many iterations, I'm converging to something which is 99% accurate. Wait, 99 or 99.99? 99.99% accurate. Okay? And if I start with something which is 60% accurate, then I converge even faster. Right? So this is like 1800. Okay? So just in a few examples, I'm boosting my accuracy just in a few iterations, I'm boosting from 60% to almost being correct all the time. And often you don't run it so aggressively, you run it a bit weaker, but it always gives you some improvement.
Professor, is delta the same as gamma in the theorem? Or?
Oh, no. Gamma is the weak learner guarantee.
Okay.
This is the weak learner guarantee.
Right.
And delta is our final sort of hope, final target.
Oh, not that delta. I meant the one equal to 0.4.
Oh, yeah, that's the gamma. That's the weak learner guarantee. Yeah.
All right, I see. Okay, thank you.
Right. So like, you're correct maybe on 60%, you're wrong on 40%. We boosted all the way to 99 point, like 99%, I think, yeah. Okay. And I won't prove this theorem here, but basically the analysis just comes from applying the regret bound suitably. There's no change you don't have to do, the regret analysis that we did for multiplicative rates already does most of the heavy lifting, and then we just have to kind of work through some arithmetic to get this bound. Okay? But the main thing is I want you to kind of internalize this idea of using learning with experts framework, even when there are no experts or anything like that to begin with. We're just using that as a surrogate to address this question of boosting. Okay? And we'll see one more example of this way of solving learning problems in, I think module 4 when we talk about graphical models. And there again, there's a completely unrelated question to do with regression, and we'll solve it using this experts framework.
I had a question about as the distribution updates. So does that mean, so if a sample has less weight to it, does that mean that the accuracy of a new weak learner trained on that distribution is going to be less for that specific example compared to examples with more weight?
It doesn't mean that it is less, but we don't know pretty much. We don't know how it's going to do on the things which are, for example, if it gives no weight to some examples, then we don't know what's going to happen. right? I trained on the things that I was wrong on in this round. It might or might not do well on the things that I was correct before, but that's okay. We don't care so much about that. Somehow the way the distribution is updating takes care of the problems that kind of you're raising, right? You know, what if my new learner kind of is completely wrong on the examples that it ignored before, right? But the regret analysis tells you that that doesn't happen. In fact, you know, there's something magical about this update which makes sure that you never completely lose what you gained so far.
Okay.
Okay. I mean, in some sense, that's why we don't make such a harsh update. We do a multiplicative update. Like instead of zeroing out the weight on the things that you are correct on the previous round, you decrease the weight a little bit and then you increase here and so on. Okay. All right. So any other questions about boosting or multiplicative weights or the, like, you know, regret minimization in general?
I think I still had a question about like unseen, like x's. So in the case of this multiplicative weights, I feel to know the distribution over your x of like the dth data point, then you have to know what the y for that dth data point is in order to know how to update it in order to get the loss. So if we were given, say, a new face to classify that we don't know the label to, how would we like use the weak learners?
So basically we use the weak learners to compute h, right? So we computed this hypothesis h, okay? And now whenever I get a new face, I will use h on it.
Okay.
Right? And I mean, in the way we phrased the question of boosting, we only asked for the booster to do well on the samples, right? So we only asked it to do well on samples, but there's a theory of generalization which tells you that if you can do well on the samples with a not too complicated a hypothesis, then you'll do well on unseen examples.
I see. So for an unseen example, how would we use this majority of like h0 through h of t minus 10?
Oh, okay. So maybe one thing is not clear is what the weak learner gives you is a predictor, right? It's a function, right? So now each ht is a function from domain to labels. It's defined on the entire space. It's accurate on, it gets some guarantee with respect to the d's, the d0, d1 and so on, but it's defined on the entire space. So think of this as some kind of parameterized family, right? It gives me some parameters which has some guarantee on how well it does on my training data set.
Oh, okay. Okay.
You should think of this, you should think of the data set as a training data set. And I have the ability to get 51% accuracy on subsets of the training data set. And then I'm saying I can combine them to get 99% accuracy on the training data set.
I see. Thank you.
Okay. Yeah, that's a good question. Like, you know, that's why I didn't go into the full like pack learning framework and only focused on improving the accuracy on the training data set, which is our data set here. Okay. Any other questions?
I guess following up on that, like not to delve too deep into the generalization piece of it, but there seems intuitively there should be like a trade-off between the number of samples that you use and how well it generalizes.
Right, so maybe not the number of samples, but the number of iterations you run. Number of samples as well, but also more, I think, you know, the number of iterations also makes a difference. Okay, so in particular, one of the things to note here is that I'm saying number of iterations because I don't know if there's something called VC dimension, and that's a way to control generalization, right? And the fewer iterations you run, the better your generalization guarantee is. Basically, the number of the generalization error kind of grows linearly or slightly worse with the number of iterations you run. If that makes sense. Because the BC dimension kind of scales with the number of iterations. And there's a whole rich body of work on trying to get around these kinds of issues. What if I want my combiner not to be a majority but something even simpler? When can I do that? What if I have some other assumption on my weak learner just besides being accurate? Can I exploit that and so on? Okay. Any other questions? All right, so that's what I wanted to say about boosting, right? And online multiplicative weights in general. For there's also the end of online learning segment of this course. We didn't do the final analysis of Ada Boost, but as I said, I'll post a reference for it. And going from the current analysis of multiplicative weights that we did to the full analysis is not that much more complicated than what we already did. Okay, so in the remaining 5 minutes, I won't go too deep into the next section, but let me at least sort of get started with the main problem that we're going to study for the next 3 or 4 lectures. So the next section is going to be on what is called the principal component analysis. Okay, so it's kind of very different from the first 2 portions of the course so far. One, we started out with this learning as empirical risk minimization, right? And then we just dug into optimization as our end goal. We forgot all about learning. We just focused on how to optimize functions using as simple an assumption as possible. And our assumption was, okay, we can compute gradients, right? And that was it. So that led to gradient descent, stochastic gradient descent, Nesterov accelerated gradient descent. And then online learning kind of led us to another important algorithm, which was multiplicative weights update and multiplicative gradient descent and relatives. And now we're going to switch gears and talk about another very important algorithm in data mining and especially unsupervised learning. And this is often the first step in many data pre-processing routines that people use. Okay, so this corresponds to, this shows up in unsupervised learning. Okay, so what do people mean when they say unsupervised learning, right? So unsupervised learning, one way to think about it is meaningful feature extraction. That's not the only way. I mean, there are many, it's a whole field by itself. But suppose I give you a set of unlabeled examples. There are no labels associated with any example. I just give you a billion images, that's it, nothing else. I'm not telling you this is a picture of a dog, this is a picture of a cat, anything like that. I'm just giving you a million or a billion pictures. What can you learn? What can you extract from this? Right? So one thing that people often do is to sort of find succinct representations of the space. I might give you each vector is maybe 1,000 dimensional or has a million dimensions, right? But maybe most of them are kind of irrelevant values that don't affect my downstream learning tasks, right? So then what you can do is to sort of represent each example with fewer features. Okay, and usually the goal is to do this in a way so that you don't affect what happens in downstream applications. So that's one unsupervised learning and feature extraction. And we'll see one of the most often used ways for doing this. So basically there is an algorithm which we'll see, it's called principal component analysis, which you can give give it some representation like this and a number k, okay, and it gives me back a n by k matrix. So it reduces the number of features from whatever you started out with to k dimensions, where k is an input parameter. So that's it. It's going to be a meta algorithm which will do this. And this is often the first step before you start doing your sort of regression, logistic regression, or maybe even some kind of more complicated neural networks. And the other application we'll see, PCA is also useful for something called matrix completion or collaborative filtering. Okay, so at first look, this idea of feature extraction doesn't seem to have anything to do with the next application I'm talking about. But it turns out the same algorithm is also a very good first step for solving this question of recommendation systems or collaborative filtering. So what's the problem here? The problem here is the following. Now suppose I have the Netflix, I'm Netflix and I have all the data about all the users and the movies. And imagine your favorite movies and the most hated movies of all time, right? Both line by line. And each user rates some movies, right? Now you can just like or dislike a movie, but back, maybe a few years ago, you could actually pick a number for how much you liked a movie. Like you can give it 1 star, 2 star, 5 stars, right? Because maybe I rate this movie 5, this movie 0, 1 star, this movie 5, 2, 4, so on. Okay. User 2 has some similar ratings, but there will be a lot of missing entries in that I'm not going to rate every possible movie, right? I just rate a few movies. Okay. And the goal of matrix completion or recommendation systems is to recommend movies or somehow figure out what those missing entries values should be. So what should my rating for this movie be based on my ratings as well as the ratings of everyone else in my database? Okay, it's not just specific to my rating. You also have to take into account how others are rating that movie, and maybe there are users whose ratings are very similar to mine, and I can use that, right? And principal component analysis, as we'll see, can answer both of these questions. And that's what we'll study for the next 2 or 3 lectures. And no surprise, but this will also connect back to some version of gradient descent in the end. Okay? So that's all I want to say about kind of what is going to come up for the next few lectures. But let me show one application that people did, right? It's kind of very impressive. So there's this company called 23andMe. Okay. And what they did was they took a bunch of users or a bunch of people, not users but people, and collected their DNA. And the people were not chosen at random. They had to satisfy some very strong geographic constraints. Like, set of people, collect the DNA. Okay? So each, somehow you have this, you collect DNA from each person and you map the DNA to a numerical vector in some standard way, right? So this is person 1, person 2, person 3, so on. Okay? And they pick the people based on, like they only picked people where, 2 generations up or maybe 1 generation up, all of them were from the same geographic area. That was a constraint in which they picked the people. They looked at their DNA sequences. It has like a million or so features. And then they applied PCA to it to extract just 2 features. Right? So this is PCA of X, 2. So DNA sequences are very, very long, right? Absurdly long. And they compressed all of that to just 2 features per person. All right? And then they sort of normalize it in some way just by, shifting things and kind of centering them in some way. All right? And then they did something very weird, which is to plot these coordinates on a 2-dimensional plane. Okay, and then plot on 2D, just like a scatter plot, right? This is, person 1, person 2, so on. Okay, and what happened after that is very remarkable in the sense that this is the plot that they got. Okay, so they collected DNA, they extracted principal component analysis, which is something we'll do in the next 2 lectures, and then they just plotted it, right? There's something, sort of a strange thing to do. You're just plotting things based on DNA. And what they realized was that if you look at which region these people were from, you basically recover the map of Europe. All the people who were from Ireland, for example, kind of were ending up here, which is where Ireland is approximately. You can see even fine-grained differences, right? Like all the people from France were kind of getting clustered in something which looks like where France is geographically. And you can really make out the map of Italy here, right? It's kind of a very, very strange phenomenon that if you just extract 2 PCA features from this data set, you almost recover geographic correlations based on DNA sequences. Okay? This is kind of an application of PCA, right? So this is principal component 2, principal component 1, to show that principal components and PCA, principal component analysis, can really extract, is really extracting something useful from just this giant set of features. Okay? And what we'll do in the next 2 lectures is to understand and come up with what algorithm did they use to extract this PC2 and PC1. Okay? Alright, so I'll see you all in the next class and where we'll start talking about principal component analysis. Any questions about this? I encourage you to read up on this 23andMe project because it's kind of very surprising that just looking at numerical features extracted from DNA shows you geographic correlations on the map. Okay. And I'll see you all on Wednesday when we'll start thinking about how to formalize this extraction.